At the center of everything, there is fire. Not fire the way we think of it, not wood and smoke and orange flame. Something far older, far stranger, and almost impossibly powerful. The sun is a star, and like all stars, it is essentially a controlled catastrophe. A ball of gas so massive that its own gravity crushes its core down to temperatures exceeding 15 million degrees Celsius. At that kind of heat, hydrogen atoms stop behaving like atoms at all. They collide with enough force to fuse together, merging into helium and releasing a staggering amount of energy in the process. This is nuclear fusion, and it is the heartbeat of our entire solar system. Every second, the sun converts around 600 million tons of hydrogen into helium. In doing so, it loses a small fraction of that mass, and that missing mass becomes pure energy, expressed in Einstein's famous equation: energy equals mass times the speed of light squared. The speed of light is enormous. Squared, it becomes almost incomprehensible. That is why even a tiny loss of mass produces enough energy to light a whole planet for a year. But the sun doesn't just generate energy. It also holds itself together through a remarkable balance of opposing forces. Gravity pulls inward, constantly trying to collapse the star. Radiation pressure pushes outward, the raw force of all that energy streaming toward the surface. These two forces have been locked in equilibrium for roughly 4.5 billion years. Neither wins. The sun simply burns on, steady and patient, in perfect tension with itself. That energy eventually escapes as light, but light is not one thing. It is a spectrum. The sun emits radiation across an enormous range of wavelengths, from high-energy X-rays and ultraviolet radiation down through the visible colors we can see, and further still into infrared and radio waves. The narrow band of visible light, the warm yellow-white glow of a sunny afternoon, is only a small slice of what the sun actually produces. Our atmosphere absorbs much of the rest, which is fortunate, because unfiltered ultraviolet radiation would make the surface of Earth a very hostile place. Light from the sun takes about 8 minutes and 20 seconds to reach Earth. Think about that for a moment. The sunlight on your face right now left its source before you finished your last cup of coffee. It crossed 150 million kilometers of empty space and arrived here carrying warmth, driving weather systems, powering photosynthesis, and making life as we know it possible. The sun is not merely a light source hanging in the sky. It is the gravitational anchor of the solar system, the engine that drives climate and chemistry across billions of kilometers, and the origin point of nearly all the energy that moves through this corner of the universe. Everything else in our solar system exists in relation to it, shaped by it, warmed by it. From that gravitational anchor, everything else follows, and what follows is a family of 8 worlds, each one a different answer to the same starting conditions. The solar system began as a spinning disk of gas and dust, and the planets that formed within it were sorted by heat. Close to the young sun, temperatures were ferocious. Only rocky, metal-rich materials could survive. Lighter compounds, water ice, methane, ammonia, were vaporized and pushed outward. So the inner planets, Mercury, Venus, Earth, and Mars, built themselves from dense, solid stuff. They are small and heavy and hard. The outer planets formed beyond a boundary astronomers call the frost line, where it was cold enough for ices to condense. There, solid grains accumulated faster, cores grew massive, and those massive cores pulled in enormous envelopes of hydrogen and helium from the surrounding disk. Jupiter and Saturn are the result. Uranus and Neptune followed the same path, though they captured less gas and hold proportionally more ice in their interiors. This is not coincidence. This is physics. Kepler described the shape of orbits before anyone understood why they had that shape. Each planet traces an ellipse, with the Sun sitting at one of the two focal points, not the center, a focal point, which means every planet spends part of its year slightly closer to the Sun and part of it slightly farther away. Earth's orbit is nearly circular, so the difference is modest. Mars has a more elongated ellipse, and that eccentricity has real consequences for its seasons and climate. Kepler also found something remarkable in the numbers. The time it takes a planet to complete one orbit, its period, is mathematically tied to the size of that orbit. Specifically, the square of the period is proportional to the cube of the average orbital distance. It sounds abstract, but it means something beautiful. The solar system is not random. It is structured, predictable, governed by a single relationship that holds from Mercury all the way out to Neptune. Newton explained why. Gravity falls off with the square of the distance. A planet farther from the Sun feels a weaker pull, moves more slowly, and sweeps a longer path. It simply takes more time. Jupiter, 5 times farther from the Sun than Earth, takes nearly 12 years to complete one orbit. Neptune, 30 times farther out, takes 165 years. One Neptune year is longer than the entire history of the United States. Mass matters too. The more massive a planet, the stronger its own gravitational field, and that field shapes everything from its atmosphere to its ring system to the orbits of its moons. Jupiter is so massive that it has acted as a gravitational shield for the inner solar system, deflecting or capturing many of the large bodies that might otherwise have struck Earth. 8 planets, one set of laws, and from those laws, an astonishing variety of worlds, each one a chapter in a story that gravity has been writing for 4.5 billion. But the story does not end with the planets. Beyond them lies a frontier so vast and so strange that it makes the inner solar system feel almost cozy by comparison. Begin with the moons. There are hundreds of them scattered across the solar system, and each one is a world shaped by the same forces that built the planets themselves. Take Io, the innermost large moon of Jupiter. It is the most volcanically active body we have ever found, not because of radioactive heat trapped in its core, but because of tidal forces. Jupiter's enormous gravity pulls on Io constantly, and the competing tugs of the neighboring moons Europa and Ganymede stretch and squeeze Io's interior like a ball of clay being worked in a giant's hands. That mechanical stress generates heat. That heat drives the volcanoes. It is a moon being cooked alive by gravity. Europa tells a different story. Beneath its smooth, cracked shell of ice, there is almost certainly a liquid ocean. The same tidal flexing that tortures Io warms Europa just enough to keep water liquid in a place where sunlight barely reaches. Scientists believe that ocean may be one of the most promising places in the solar system to look for life. Not life as we imagine it from science fiction, but microbial life, patient, persistent, surviving in the dark. Move outward to Saturn, and the rings demand attention. They are not solid. They are billions of individual particles, ice and rock ranging from grains of sand to house-sized boulders, all orbiting in a flat disk. The rings are maintained and sculpted by shepherd moons, small bodies whose gravity herds the particles into precise lanes. Resonance plays a role too. When a ring particle completes 2 orbits in the time a moon completes 1, the repeated gravitational nudges add up and carve a clean gap. The Cassini division, that dark band visible even through a modest telescope, is emptied this way. Order emerging from repetition. Gravity's own handwriting. Past Neptune, the solar system does not simply stop. The Kuiper Belt extends for billions of kilometers beyond Neptune's orbit, a broad ring of frozen bodies left over from the solar system's formation. Pluto lives here. So do hundreds of other dwarf planets, their surfaces coated in methane and nitrogen ice, their skies lit by a sun that looks like little more than a bright star. And beyond even that lies the Oort Cloud, a vast spherical shell of icy bodies surrounding the entire solar system at distances almost incomprehensible to human intuition. Comets that swing through the inner solar system in long, looping orbits often originate there, dislodged by the gravitational nudge of a passing star. The solar system, it turns out, is not a tidy collection of 8 planets orbiting a star. It is an enormous, layered structure, dynamic, ancient, and still in motion. The same laws that govern a falling apple govern the outermost comet drifting in the dark. One set of rules,